Last time we started discussing what happens if two atoms get close together. And we said there are two possible scenarios. Here is the distance between atoms, atom B and A and B. And here is the energy. We said that the energy equals 0 corresponds, in fact, to the energy of the atom A plus the energy of the atom B. And we are considering two possible scenarios. One scenario, that the molecules create a chemical bond and the potential energy profile looks like that depending on the distance between atoms. Another scenario was that the molecules or the atoms, well in this case atoms, they are already closed shell atoms and then they don't really make the chemical bond. They interact very weakly by so-called dispersion force. And then the profile looks more or less like that. We said that usually in both cases you can represent the energy by so-called Morse curve. Some people say Morse potential. And I gave you the formula for this Morse potential. Now I give you once again. Not that the previous one was wrong. It was okay. It was just too many constants there. You can remove one constant and nothing happens. So the standard form in the textbook is like that. D multiplied by 1 minus e to the power minus alpha r minus r0 square. Now, we said that there are few important parameters describing these potentials. One of them were this number that is D in this equation. Another one is the position of this, that is the R0, or sometimes people also say RE for the equilibrium. Both things are okay. Another parameter describes what is the curvature. Now, this is a new term for you, so I will say a few words about the curvature. Imagine this line and this line. I'm asking about this point and this point. This line looks more flat. This line looks more curved. So we say curvature is larger here than here. You can imagine this, that this line and this line is a plot of the function fx equal a times x squared. And this is another function gx equal b x squared. If you think like that, then you have two parameters, a and b. Just this parameter b has much larger value than this parameter a for these curves. So this parameter is the curvature parameter. And we say that this one has very large curvature, this one has rather small curvature. Completely flat line has zero curvature. Good. So how this curvature, the shape of the minimum, is measured for molecules? Usually people introduce something what is called vibrational frequency. And this vibrational frequency is defined by we have 0, so 0. 2 pi square root of 2 times d mu r0 square. So a bit strange definition, but anyway, what you see that this omega is proportional to alpha, and alpha is a parameter in this equation. So this one represents how deep is our potential. This one represents where it has a minimum. So it defines this point. And alpha defines what is the curvature in the minimum. In fact, not only alpha, because as you see, alpha, d, and r0, all of them are here. So it's a bit complicated definition. But anyway, this number tells you what is the curvature. So it tells you if the number will be 0, it means the potential is flat. If the number will be small, it means the potential looks like that. If the number is large, the potential will look like that. Okay, we have the mathematical apparatus to analyze molecules now. So we can go to some real system and we can understand how the real system looks like. Let's take neon 2. Neon, as you know, is a noble gas. It's number 10 in the periodic table. It's a closed shell system. Closed shell system is already happy. So when it comes to another closed shell system, it doesn't want to make bond. So that would be the orange curve. So now what we are going to discuss would be the van der Waals molecules. So let's start with the first van der Waals molecule. And we need some parameters for this van der Waals molecule. So neon 2, R0 is 3.1 angstrom. Omega is equal to 14 so-called wave numbers, and the D is denoted as D00 is equal to 0.002 electronvolt. Make it clear, I remove the Morse potential, we don't need it anymore. Just to give you idea what happens for normal molecules, also called covalent molecules. I will explain this word a bit later. So as you see, I keep two colors. I keep orange and red. The same on this plot, red and orange. So one of the covalent molecules that we can analyze would be, for example, hydrogen molecule, H2. And for H2, the bond distance is equal 0.74 angstrom. That is a huge difference, 3.1, 0.74. This is almost 4 times shorter, or more than 4 times shorter. What about omega? Omega for the hydrogen molecule is equal 4,401 wave numbers. And next parameter is D00 is equal to 4.5 electronvolt. You see the differences are huge. 4.5 versus 0.00002. Yes? No question? Right. Good. Let's go further. Another molecule would be argon 2 with, again, I'm going to put only numbers, not to write R0. The distance for argon 2 is 3.8 angstrom. Frequency for argon 2 is 26 wave numbers. And the potential is 0.01 electronvolt. For xenon 2, the potential, the distance is 4.4 angstrom. Frequency is 21 wave numbers. And the depth of the potential energy well is 0.2 electronvolt. What I did, we just analyzed 2 neon atoms, 2 argon atoms, and 2 krypton atoms. All of them are closed shell molecules. Closed shell atoms. So 2 closed shell atoms give together the van der Waals. Now what happens if you mix, xenon was the last one. What happens if you mix something which is closed shell and something what is open shell? This is an interesting question. So as an example of such molecule, we take xenon chloride, which exists, surprisingly. All of them exist, as you see. And this xenon chloride has the bond length of 3.18 angstrom. And the frequency is 26 wave numbers. And the well depth is 0.03 electronvolt. So when you look at these results, nothing really changes. First, the bond is still very, very long. Second, the potential is still very, very shallow. And the curvature is still very, very small. So mixing closed shell atoms with open shell atoms doesn't really give you the chemical bond. You need 2 open shell atoms. Sometimes, like for example the xenon oxide, it turns out that here you get infinity. And here you get 0. What does it mean? We just take these examples in green. And it means that if I plot the green line doesn't have minimum at all. It's immediately going up. So there are such situations too, you have to remember. But most of the closed shell system interact with each other, giving very long minima. Good. You can ask me if only closed shell systems are giving van der Waals molecules. The answer is no, not really. For example, if you take manganese dimer, the equilibrium distance for manganese dimer is 3.4 angstrom. I don't remember what is this one, but it's around 90 wave numbers. Whew. I don't remember that one at all. But still, you see that this is rather small and this is very long. What is special about this? The problem is that manganese is not closed shell at all. If you write down the electronic configuration of manganese, you find that it would be argon, and then you have 4s2, 3d4. But in fact, that is a plausible version, but not true version. Turns out that if you take one s electron and put here on d, this is lower in energy. So really it's 1, 5. To understand this, you have to remember that the energy of the 4s orbital and the energy of the 3d orbitals are almost the same. Second, 4s2 means that I put 2 electrons here and 4 electrons here. This is not very symmetric. If I take away this electron from here and put it here, this looks more symmetric. Of course, this is not a reason for anything. Chromium. Sorry, chromium, yep. So for chromium that would be like that, yes. But no, what I really wanted to discuss is manganese, so come back to manganese. And let's change what I wanted to say here, too, like that. So it's okay now. We don't need this explanation. Everything is okay. Right. So this one is a closed subshell. But this one is not closed. It's half-filled. Turns out that these half-filled subshells are also kind of happy. They don't like to react too much for the case of the d electrons or f electrons. So they also make a van der Waals molecule. Generally, it's very difficult sometimes to find when you have van der Waals and when you have a real molecule without checking the reality or doing the calculations. Good. Let's go to the real molecules now. And the real molecules, I have another example, would be the CO molecule with the RO equal 1.1 angstrom, frequency equal to 2170 wave numbers, and D0 equal 11.09 electronvolt. I give you this example of the CO because CO has probably the largest bond energy. So making from carbon and oxygen atom CO molecule gives you the lowest minimum out of all possible diatomics. So somebody can ask me, what kind of possible molecules are possible to be made? Can I make all possible combinations? And the answer is yes. This book contains only diatomic molecules, 2 atoms molecules. And this is the list of numbers, just one big table containing all the data about CO, CN, HH, mercury dimer, mercury argon, KF, KI, O2, PTO, all possible molecules. Unfortunately, this book was written in 1978. So the only data are 30 years old. Last 30 years, there's a lot of new results. Probably if somebody writes this book today, there would be this size of book. Unfortunately, nobody writes. The guy who wrote the book got the Nobel Prize. Not for the book, but yeah. So we can check any molecule we want. For example, what we want to check. So first what we should realize is this is N14, means that the mass number is 14. Okay, that's correct. Now it starts from D00. D00 is 9.7 for this molecule. And then you have a lot of different strange stuff, and all these strange stuffs are excited states, and X, the last one, is the ground state. So we found that the distance is 1.097, this is the distance, RE, and the omega is 2,358. So using this book is kind of easy. But you can show some strange molecules, for example, like, one atom of gold and one atom of cobalt, which nobody cares. And people only know what is D00. No other data are available for this molecule. If somebody wants to have a look into the book, just feel free. So now you already know that the bond lengths are very large here and small here. But now, what are the bond lengths that you can meet? The shortest one is shortest. Well, the shortest for the smallest atoms. And the smallest atom is, of course, hydrogen. So this is the shortest you can ever think. Shortest. Longest. Now it's difficult, because if you think about these numbers, and these numbers, and if you go in the direction of the van der Waals molecule, probably you can find molecules that have the minima somewhere here, and finally go here. And it's true. So it's very difficult to define what is the longest, because these covalent molecules very slowly will transfer to the van der Waals molecules. You can find all the way. So we probably define the longest one, R0, as around approximately 3.5 angstrom. This is around the van der Waals. Now the omega. This is the largest possible, 4,400. And the smallest possible, you see that they can go as low as 10 wave numbers. D0, I said that this is the highest possible. And probably the lowest possible is around here. You cannot go really much lower. Good. Another important thing to know is where or what is the distance of some normal bonds. Let's say HH, we already know, is 0.74 angstrom. Let's say our carbon-carbon single bond would be, everybody answers, don't worry. 1.5. Okay, since the answer 1.5 was a very good answer, I can tell you that the answer to your questions is in the table 2.4, which is giving the average bond lengths for different pairs of atoms. So carbon-carbon is 1.54. And carbon-carbon double bond is 1.34. And carbon-carbon triple bond is 1.20. And carbon-carbon 1.5 bond you can ask me what is 1.5 bond, and I will explain in a moment, is 1.39. Okay, we came to the moment when we have the half bond. Sounds strange. In the high school they are teaching that there is single, double and triple. What is half bond? No? No answer? Okay, we'll explain in a moment. But this thing, half bond, is probably telling you already that bond order, so number of the strokes I'm putting here, is not a very well-defined quantity. And it's true. Very often it's not well-defined quantity. And we will explain what does it mean 1.5 bond in a moment. But to give you example where you have 1.5 bond, take a benzene molecule. Six carbons, 6 hydrogens. And usually people are writing this that way. If this is true, then this is double bond with the length 134. And this is a single bond with the length 154. So really, the molecule should look something like that. The question is, does it look like that? And the answer is no, it doesn't. It's perfectly symmetric like that. So the correct way of writing these 3 double bonds is to answer that these 3 double bonds are everywhere in 6 positions. So the only thing I can do is just put half everywhere. Like that. Another way of putting half bond that way is making a circle here. And these are called aromatic compounds. Okay, let's continue. So you have an example of the molecule with 1.5 bond, benzene, with the bond level 139. Next answer. Is it true that if carbon-carbon bond is 154, then if I draw 2 molecules, let's say CH3, CH3, and for example, what? COH, CH2OH, CH2OH. Does it mean that this single bond and this single bond have the same length? And the answer is no. Every molecule has different length. They are similar, but not very similar. So here, I believe it would be 154. But in this case, I believe it would be 156. So it's really changing. These results are the average result. Good. Another thing, we discussed bond lengths, now let's discuss bond energies. Let's take the energy of the CO bond. And again, you can go to the table number 2.3 in your books, which is giving average bond dissociation energies. And for CO, we find that the average single bond is 360 kilojoule per mole. This brings us the first problem. The problem is that as so far we are discussing the bond energies in electronvolts because that's what the book gives. And now we have another unit, kilojoule per mole, so we have to transfer one unit into another. You should remember that 1 electronvolt approximately is 100 kilojoule per mole. So this one is around 1,100 kilojoule per mole, around, not exactly. Okay, go further. C double bond O gives us what? 743 kilojoule per mole. Nice. So what we can do, we can now open some molecule. For example, let's take a molecule, this, carbon oxide. And we can find what is the energy of dissociation, 1 carbon and 1 oxygen atom, from the table 2.2, for example. And this energy, D, for this molecule is given to be 1,062 kilojoule per mole. Which kind of gives you the feeling how good are the average values. If these average values are good, then this value should be the same like this. Because this molecule has one double bond between C and O. But the difference is 300. The accuracy is only 60%. So you see that many molecules, even if they have double bonds, carbon, oxygen, the energy of these bonds can be very, very different. Good. As so far we discussed how the atom and atom are reacting. Now we should also discuss how the ion plus ion are reacting. An interesting case would be also ion plus atom, but this is kind of the same family. So let's make some space. And now let's write the most possibilities. One is plus reacting with plus. Another one is minus reacting with minus. Another one is plus reacting with minus. It's kind of clear that in the first two cases you get repulsive potentials. In this case, you get attractive potential. And if you think about a moment, if you plot the energy of this attractive potential, you probably just follow Coulomb's law, and the potential should look like that, going to infinity. But it doesn't make sense, because if the two ions are getting close and close and close together, at the very close distances, the proton starts to repulse, and finally the potential looks like that. So it has the same part like for atoms, the short distance part. So again, we get a similar shape of the potential like we get for the atoms, but now the equation is a bit different. The equation is called Born-Mayer equation, or Born-Mayer potential. And this is equal potential some constant So this is a good model for interacting of two ions. There is one big difference between interaction of ions and atoms. One huge difference. And the difference is, if you have a closed shell and closed shell atom interacting, they make the van der Waals complex, but everything is closed shell at the end. And not electrically charged. If you have open shell and open shell atom reacting, they make a closed shell molecule, which we define probably in next class. And again, everything is closed shell and not electrically charged. When we have two ions reacting, these ions come together. Usually they are closed shells, so it's not a problem, but they have electric distribution that is very different than the distribution of atoms. It means one is plus, one is minus. This plus wants to attract another minus. This one wants to attract another plus, and so on. They start building larger and larger. That's why we don't have molecules in the ionic bonds. Only solids, only crystals. So, ionic bond only in solids. What does it mean? It means that two atoms is not enough. It means that you need 1,000, 2,000, 1 million atoms to make a solid. How it looks like? Very simple. Plus, minus, plus, minus, plus, minus, plus, minus, and so on and so on. This is one-dimensional model, but hardly ever happens. Usually they do two-dimensional, minus, plus, minus, plus, minus, plus, minus, plus, or they can make a three-dimensional model when we have here another minus, here another plus, minus, plus, minus, plus, minus, plus, another plus, minus, plus, I missed something. Here three minuses in a row. Minus, plus, minus, plus, minus, plus, minus, plus. So it should be minus, plus, minus, plus, minus, plus, minus, plus. And you see that they start building the crystal. Wow. Difficult to imagine. But if you have a cube, then one way of writing that would be putting a positive charge here, then putting another one here. That would be positive, and the negative are between them. And so on and so on. And building out of these blocks, you can block a crystal, ionic crystals. So we defined one type of bonds, which are ionic bonds. These are bonds made in a solid between ions. Okay. What are other types of bonds? We have ionic bonds. Another type of bonds would be covalent bonds. Another type of bonds that we already discussed are the van der Waals bonds. Another type of bonds are so-called metallic bonds. And last type is the donor-acceptor bonds. How many minutes are left, by the way? 2. Good. Usually I ask after time, so. Good. We should define all of them. I think this one we already defined. What are the van der Waals bond and what is the mechanism of interaction in the van der Waals bond in the last class. Metallic bonds are kind of easy to think about. Metallic bonds happens only in solid. And the metallic looks like that. You have atom, 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 atom. Not ions this time, just atoms collected together. And now each of these atoms gives 1 or 2 electrons outside, whatever it means. And these electrons, they can travel in all the possible structure, in all the solid. It means that 1 electron and the atom, they are not connected together like in a molecule. The electron belongs to all atoms at the same time. So the electrons make a soup. But with the difference that in physics nobody is using the word soup. Usually they say electron liquid. So electron make a liquid, and inside the liquid the nuclei are hidden. Okay, and we are going to finish today the class in this moment.